Welcome back to the second video on Chapter 5. Before we get into the next section, I wanted to remind you where we left off in the last video. We were talking about annualizing rates of returns. And you'll want to remember that there are two primary ways: APR, or annual percentage rate, and effective annual rate. And a key difference is that APR does not recognize compound interest, while effective annual rate does uh, uh, recognize compounding. So, and the difference between the two will grow larger as the number of compounding periods in a year increases. So, if an instrument had interest that compounded daily, there would be a much larger difference between the annual percentage rate and effective annual rate on that instrument than if the interest compounded, let's say, monthly. So, for some reason, instruments that have regular cash flows throughout the year that occur at regular intervals, like mortgages and bonds, are usually quoted as annual percentage rate, is the way their returns are quoted. But the problem here is that it's difficult, or it's not a level playing field to compare two instruments that have interest that compounds a different number of times per year. So if you take that instrument that compounds daily and compare it to an instrument that has interest that compounds semi-annually, that's not very comparable. So you have to convert both APRs, that of each of those instruments, to effective annual rate so that you've got an apples to apples comparison. So that's the reason that we use that interest rate conversion on the calculator and convert APRs to effective annual rates. Another issue that impacts returns, we're studying the issues around the return you earn on an investment. And another issue that impacts that in a major way is inflation. So there's a guy named Irving Fisher in the 1930s that came up with what's become known as the Fisher equation, and this is kind of a rearrangement of his formula he initially introduced. And first of all, let me just explain what inflation is. The textbook says the inflation rate is the rate at which prices are rising, and we measure that with the increase in Consumer Price Index, or CPI. So another definition is that inflation is the general increase in prices of goods and services and the general decrease in the purchasing power of the currency. Now, I want to emphasize too that inflation is a domestic issue. When we think of the prices of things going up, we have different inflation rates in different countries around the world. So one country, for instance, Venezuela, may be experiencing 2,000% inflation, while Europe is experiencing 2%. So it's a domestic occurrence. It varies by country. Now let's define our terms here. And we use R in this equation, and you'll see this if you Google around on the Fisher equation. Different nomenclature here is used, but we've got here R, capital R, is the nominal interest rate. Now that's the published rate. If you see a bank sign flashing 3% on CDs, that is the nominal rate. Okay, and the nominal rate, Irving Fisher said, is really made up of two components. Part of that nominal return is inflation. The prices of goods go up over the year that you would earn that 3%. So that piece is the inflation rate. The other piece is called the real rate of return, or the real interest rate. So the real rate is the part of your return you earn after deducting inflation. So it's to be precise, it's not really deducting it. Instead, to get our real interest rate, we take the nominal rate right here, 1 plus the nominal rate divided by 1 plus the inflation rate, and that gives us R, our real rate of return. Here's an example here at the bottom. We've got a nominal 10%, 1 plus 10%, divided by 1 plus the 5% inflation rate, and we find out that the real interest rate or real return is 4.8. Now, it gets you very close to just subtract inflation from the nominal rate. 10 minus 5 would give you a 5% real return, but when you actually run it through the correct equation here, you come out with a real return of 4.8%. Here's the actual equation that Irving Fisher introduced in the 1930s right here, which is the one we just looked at is a rearrangement of this Fisher equation. And in this case, he solved for the nominal rate, R. In the last slide, we solved for the real interest rate. Here we're solving for the nominal rate. And in this case, it is the real rate plus the expected inflation. Expected, not historical, but expected inflation. This chart kind of intuitively validates the fact that interest rates do track inflation, includes the inflation component, because we're looking at T-bills here, which, as you know, are a risk-free investment, so we have no risk. But as inflation, the black line, trends upward and downward, so does the T-bill rate, which would lead us to believe that the T-bill rate does include a return for inflation. At least, as this slide points out, since the 1950s, inflation and rates, nominal rates, have moved together. Before that, there was a lot of volatility, and they did not track so closely. So I'll pause here and summarize what we've covered in Chapter 5 so far. This chapter began with trying to understand return on investment, and we opened up talking about various ways to measure return. We covered the arithmetic return, geometric return, and the dollar-weighted average return. Then we compared annual percentage rate to effective annual rate, one that recognizes compounding, the other does not. Then we just covered inflation and real returns. So real returns are essentially the return, the increase in purchasing power. So if you had $100 and it bought 100 loaves of bread, and a few years later you have $200 and it still only buys the same 100 loaves of bread, you've gained nothing in purchasing power. You've had no real return. So what we're really looking for here is to gain in purchasing power, right? So that after inflation return, real return, is what we're interested in. So now we're going to move to risk. We've talked a lot about return. We're going to talk about risk and how risk impacts return. When we talk about risk, the thing that we're concerned about is, what return might we expect on a particular investment? Because risk impacts that, right? We may fall short of the return that we expect or that we hope for. So the way traditionally that is looked at is we analyze as we come up with different scenario analysis. What range of returns do we expect, and what's the probability of each? All this is based on the idea that the markets have the returns in the markets or on investments are normally distributed, and we're going to talk a little more about that they follow a bell curve. And there's some detractors say that returns in the markets do not follow a bell curve or normal distribution, but for now we're learning traditional finance and investing, and we're going to assume that they do follow a normal distribution. So scenario analysis, you've probably seen before. You develop a range of different scenarios and the likelihood of each. And in each scenario, what is our expected holding period return? What do we think the return is going to be? Yeah, and the possible probabilities. What is the average or mean return that we expect? And then we get into a little statistics with variance and standard deviation. Standard deviation, if you can calculate variance, standard deviation is simply the square root of that variance. So let's go a little deeper on this. So not going to require you to calculate variance or standard deviation. It was covered in my Financial Management 2 classes. We covered this, and it's not difficult to calculate variance. And this little chart, you could walk through the calculation of variance, standard deviation, but I'm not going to take, because it would take too much time for me to walk through this and all the content we've got to cover. I'm not going to take the time in this class, but you can see for the stock market, in this case, we're looking at the overall stock market. We have assigned a holding period return under various economic scenarios here. Recession up to a boom period. We think in recession, the market may drop 37%, and a boom gain 30%, and a probability of each. So we could walk this all the way through, and I'd love to do it. I just don't want to take your time for that right now. And end up with a standard deviation across all of these various economic scenarios. If you're interested in this, this is more detailed and explained beginning on page 117 in the textbook, and I encourage you to go there and learn more about it if you're fascinated with this. So first of all, like I already mentioned, all of this is based on the assumption that the market's returns are normally distributed. Now, I question this. In fact, I'm reading two books right now. One is called The Black Swan, and the other is The Tao of Capital. That this is their whole thesis. They do not believe that the market's returns are normally distributed. But we'll stick with this for now. And hopefully I'll have some time to talk about the black swans. At any rate, so the two formulas here, which you will not have to know or be able to calculate, are useful because they allow us to understand normally distributed return. If returns are normally distributed, we can plot them like this on this chart. So this is an investment or a portfolio that has a return of 10% and a standard deviation. You should know that nomenclature there. Standard deviation of 20%. So we know the normal distributed return, the mean is 10%. So we're able to plot that right here on this normal distribution. And then we know that one standard deviation equals 20%. We can add 20 right here to that 10. Sorry, this does not look a little bit better. But 10 plus 10. No, it's not 10, it's 20. Standard deviation is 20. So 10 plus 20 is 30. So one standard deviation from the mean right here would mean if we have a positive one standard deviation occurrence, we would expect to return 30% on that portfolio or investment. Two standard deviations, we add another 20. So it's 20% per standard deviation. And one more, we add another 20. And so our 3 standard deviation positive event, we would expect 70% return. And statistics tells us that a 3 standard deviation event above and below the mean should capture almost 100% of all possible outcomes. Okay, now this all assumes a normal distribution, and therein lies somewhat of a flaw in my opinion. And this works on the negative side as well. 10% mean minus 20% standard deviation gets us to negative 10 on a negative 1 standard deviation occurrence or outcome, and then you would subtract another 20% to get a negative 2 standard deviation outcome. Now, so, of course, the fly in the ointment is what causes these positive and negative outcomes? Well, all sorts of things, right? We can have macroeconomic events. Some country starts a war, invades another country, coronavirus, financial meltdown, or there's positive outcomes. Central bankers lower interest rates, or economic boom times causes us to have occurrences on the positive side of the curve. So the fly in the ointment, I was talking about the book, The Black Swan. It was written by a guy named Nicholas Taleb, Nassim Nicholas Taleb, and he's widely thought to be almost a prophet. He's a very wise person, been very successful in investment, but he says, like a number of others, that this is called the tail of the curve on each side. And he says the tails are much fatter than a normal distribution portrays. And that these fat tails, the possibility of a 3 or 4 sigma event occurring is much greater than would be you would expect with these percentages that come along with the normal distribution. And that they have a tremendous impact on your portfolio outcomes. So this fascinates me, and I believe that we need to find tools to hedge or protect, buy some insurance against these negative, what's called a black swan event. So most swans in nature are white, black ones are very rare. So these fat tail events are called black swans. And I've come to believe that they occur much more often than normal distributions would predict. And by the way, if you're interested in this black swan idea, probably a book I would recommend first is called The Tao. That's D-A-O, The Tao of Capital, written by Mark Spitznagel, one of the most successful hedge fund managers that has developed an investing approach specifically around protecting against black swans. And he gives you a great history of something called Austrian economics. He talks about Austrian investing, which is all about investing to protect against these huge losses that might happen in these unusual black swans that may crop up. But back to our textbook here, that normality over time, when returns over very short time periods are normally distributed, holding period returns up to a month actually are not quite normally distributed, but they're close enough that we can treat them as normal. Couple terms I would like you to know is kurtosis and skew. So kurtosis, is a measure of the fatness of the tails, okay, on that normal distribution or any probability distribution. So there are other distributions, by the way, besides the normally distributed ones. But the normal distributions are the most fashionable, let's say, in investments, in the investment world. So if the tails are fatter, like the black swans I just talked about, then a normal distribution would indicate, then we would say we have positive kurtosis. And I think that there are, and then that we do have positive kurtosis. And then the skew is the fact that sometimes the left side of that normal distribution is higher than the right or the opposite of that. I'm going to go back to the last slide and show you what I mean. That a normally distributed, starting with a normally distributed curve, if we said that if our observation was actually more like that, that's positive skewness. If instead it's more like this, that is negative skewness. So we've got a fatter left side or right side, and so we may negative skew would have this kind of curve on the left side, but we'd maintain the normal kind of distribution on the right side. That's negative skewness. So the author of the textbook points out that scenario analysis that we began our discussion here on risk, discussion of that, is derived from historical returns. And the same with variance and standard deviation, or risk measures. They come from a time series of returns. And here's the formulas for variance and standard deviation. Again, you don't have to know those, but the objection here is that we have to ask the question, does historical returns and historical variance reflect the potential for what could happen in the future? And that's the whole point of Taleb's book, The Black Swan. That black swans are things we cannot anticipate. Some country drops a nuclear bomb, that sort of thing. So it cannot be anticipated, and therefore these time series of historical returns are of little use in predicting what the markets or an individual security or portfolio, what may happen to it in that type of extreme event. Another term that's common in investment, in the investment space, is called value at risk, and you need to learn to recognize this nomenclature. VAR is value at risk, and that is measuring the potential loss, the worst loss at a given probability. So at, say, a 5% worst case negative event, what would be our loss in the worst 5% of cases? Again, this is still based on normal distributions. All of this emanates from normal distributions, which is, in my opinion, underestimates the probability of those black swans or fat tails. So at any rate, this, I suppose, the best we have right now. We're going to stop here. This video is getting a little lengthy, and we'll pick up the rest of our discussion on risk and returns in our next video. So in the meantime, spend less than you earn, okay? See you next time.